probabilities. So you have 5 flags cast. So I want to know what's the probability that exactly 3 of the numbers shown are 4. So I'm going to roll this die 5 times. I want to know what's the probability that you get at least, so exactly 3 4s showing up. So the sample space here, sample space 30. What? Is it 30? 30? Is that right? No, so for the sample space, what you're doing is you're taking, let me write it like this actually. So take this set, so 1, 2, 3, 4, 5, 6. Okay. You're going to take this set cross itself 5 times. So you're going to, this would actually be what the sample space is. Okay. So remember, if we have a set, you have like x squared. It's x times x. This is a set of ordered pairs. Set A, B, where A and B are in x. If I write something like x to the 5th, that's x cross x cross, we did this 5 times. Okay. And this would be the set of these ordered tuples, so A, B, C, D, E, where A, B, C, D, and E are all in the set X. Okay, if I wrote some set to the 6th power, you do this 6 times. And here would be the set of all of these sequences, A, B, C, D, E, F. They're all of these finite. So when I write this sample space as this set 1, 2, 3, 4, 5, 6 raised to the 5th power, it means you take this set times itself 5 times. So when you take a set times itself, you're just getting a set of ordered pairs that you can form from that set. So when I write that set to the 5th power, it's the set of all these sequences A, B, C, D, E, where these numbers A, B, C, D, E are coming from this set 1, 2, 3, 4, 5, 6. So this is the set of all of the sequences like this, where these numbers could be any of 1, 2, 3, 4, 5, or 6. Right? So if you've got like 4, 2, 1, 1, 6, then this would be like you roll the die 5 times. The first time it was 4, the second time it was 2, the third time it was 1, and the 4th time it was 1, and the 5th time it was 6. Okay. So this is the sample space. So I want to figure out how many of these sequences have exactly 3, 4 showing up. So you think of this this ordered tuple as having like slots. Okay. So I've got 5 slots here. So I want exactly 3 of these to be 4s. Okay. So you choose 3. So you choose 3 of these 5 slots. 5 slots to fill with 4s. So you're going to just choose 3 of those slots, and you're going to put 4s in those slots. Okay. So let's say you put, so how many ways are there to do this, to choose 3 of these 5 slots? So what would you write if you wanted to write down how many ways you can choose 3 of these 5 slots? 5 choose 3, right? So you can do this in 5 choose 3 ways. So first you will choose 3 of these 5 slots to fill with number 4. You can do that in 5 to choose 3 ways. Okay, so once you do that, then you fill in the remaining slots. With either 1, 2, 3, 5, or 6. So I'm going to choose, let's say I chose this first one to put 4, this one to put 4, and this one to put 4. Okay. So I put a 4 here, here, and here. So how many choices are there for the thing that I'm going to put in this slot? 5. So there's 5 choices here, right? So I can put either a 1, a 2, a 3, 5, or a 6 here. Okay. How many choices are there in this last slot? 5. Okay, so total there are 5 choose 3 times 5 squared ways of forming a 5 tuple where the number 4 shows up exactly 3 times. So I want to find the probability that exactly 3 of the numbers that you roll will be 4s. Okay. So what I did was I went over here and I figured out how many ways you could get a 5 tuple, right? So a 5 tuple like this, where exactly 3 of these slots are filled with 4s. Okay. So I just calculated that there would be this many 5 tuples like that. Okay. So let's. You guys have any questions on how I found this number? So let me call the event E. Let's let E be this event. The event. That exactly. Exactly 3 of the rolls show. So I just showed that this number of objects in E. So I just calculated the number of ways you could roll exactly 3 4s. Okay, this number is 5 choose 3 times 5 squared. So and I want to know how many objects are in omega. So I want to know how many objects are in the sample space. Right. So the sample space was all of the 5 tuples you can form, where you can put any of the numbers 1 through 6 in these slots. Okay. So you have 5 slots here, and then you have 6 choices for each slot. Right. So how many things are going to be in omega? You guys know?
Times 6.
That's close. That's really close.
65.
I think so. So you have 6 slots, right? Right.
5 slots.
No, it's 5 slots. So I think you're right this time. So there are 5 slots. And you do this 6 times. So you have 5 times 5 times 5 times 5. So it's 5 to the power of 6. Is that the first one? Yeah, that's right. So you have 5 to the power of 6 now. So if you want this probability, so you take the number of objects in E, and you divide it by how many objects are in it. So you're going to have 5 times 3 times 5 squared divided by this thing. No, is that right? Yeah, so you have 5 slots, right? So you have 5 slots, and you have 6 choices in each slot. So it'd be 6 times 6 times 6 times 6 times 6. So I think it is 6. Do you guys see why? So it's, I think this is actually 6. Because you have 6 choices here, right? 6, 6, 6, 6, 6. So this would be 6 as the. So if you divide these, I think this is like 0.03. Do you guys have any questions on this? So here I used, when I found the probability of this in E, I used this egalitarian probability function. So the egalitarian probability function says you just take the number of objects in your event and divide that by the number of objects in the sample space. So the reason that I'm using this egalitarian probability is that this is a compound experiment, so you have the compound probability function on this experiment. Okay? But it turns out that the compound probability would be the same as the egalitarian probability. Okay? Just like if you just rolled 2 dice, right? So, let's go like this. So if you rolled 2 die, so you have, let's make this, toss 2 coins. So, you toss this first coin, you head to tails. You toss the other coin, heads, tails, and tails. Okay. So, the compound probability, so if you had a probability here, so you had all these, right? Then the compound probability would be, if you want to find the probability of getting HH. Okay. So if you're using the compound probability function on this sample space, and you wanted to find the probability of this outcome, then you would just multiply this times this. You have A times C. So the compound probability function is when you have a tree diagram of your experiment like this, and you want to find the probability of an outcome, you just multiply these probabilities on these branches. Okay, that's the compound probability. Then the egalitarian probability. If you wanted to find the probability of this thing, then all you do is you count up how many objects